Dealing with analog signaling for FXO or FXS, there's three different main types of signaling: supervisory, address, and information. Okay, the supervisory signaling either uses loop start or ground start. It's important if we're using ground start to make sure that you actually ground your equipment. So if you're using a voice gateway, an iOS router, there is a ground lead on every iOS router. It needs to be grounded to true ground. Okay, so maybe to a water pipe that is, goes deep in the ground, or else something that goes deep into the earth. Otherwise, if you don't have a common earth ground, then guess what? The telco's circuit will be grounded, so you should just ground yours to theirs, but you won't have a common ground, and your electrical signaling will be completely messed up. More commonly used is loop start. One of the reasons we don't have to properly ground everything. It's still a good idea, but we don't have to properly ground it for loop start to work. And the way that these supervisory signals work is they're caused by differences in voltage and or grounding on the tip and ring wires. For address signaling, very, very, very old phones. Most carriers don't even probably support it anymore. Maybe they do. I don't know. Haven't tried. But one way of signaling address or the number we want to call for analog is pulse. So if you ever remember seeing or hearing about a rotary phone that used pulse dialing, that was pulse dialing. Or the DTMF, the dual tone multi-frequency, is obviously what most people have used since the 50s, 60s, and still used today. And then information signaling, information about what's going on in the call, our call progress tones. So for instance, I go off hook, that is, I pick up the phone. When I go off hook, I get a call progress tone telling me it's okay to dial. That's called dial tone. Then I make my call, and I hear another call progress tone called ringback. That's telling me that on the other side, it's now ringing. And I know that for a fact because the telco's told my phone through these electrical pulses, through these electrical loop start or ground start supervisory signaling, that it's okay to go ahead and tell your calling party to play ringback because we are now ringing or alerting the other side. Or busy tone or reorder tone, those are all call progress tones. So let's take a look at common configuration for FXO and FXS. FXS voice ports, we have the signal command, which by default is signal loop start, but if we need to change it, we can, and again, you would know because the carrier would specify, we could change it to signal ground start. CP tone, this is call progress tone, and this is by country. This is because ringback or ringing, if you've ever traveled abroad and used a landline or possibly even a mobile, you have certainly invariably noticed that, instead of sounding like whatever it is you're used to in your own home country, it very well possibly sounds different. And then also ring cadence. So the cadence or the pattern with which the ringing is done, we certainly have the ability to change this to a number of preset ringing cadence patterns. So we'd say ring cadence pattern, and then we would specify the pattern number. Do a question mark to see the available patterns there. For an FXO, we have signal again, loop start or ground start, and then connection PLAR, and then OPX. OPX stands for off-premise extension. So connection PLAR, OPX, and then whatever number or DN we want it to look for. So again, FXO, this would be coming in from the PSTN. Obviously, if we're dialing out, this doesn't have any effect. But if a call is coming in from the PSTN on an FXO port, connection PLAR OPX tells it where to ring to. Basically provides the DNIS to match the outbound dial peer. FXS DID, we will almost always say signal DID wink start, but and we'll talk about wink start versus immediate start versus delay dial. But we'll, if the carrier provided a different one, then you might have a different DID signaling. So let's look at analog signaling for E&M, ear and mouth, or earth and magnet. Supervisory signaling, there are 6 different types, type 1, 2, 3, 4, 5, and SSD C5. Again, these are caused by differences in voltage and grounding, but not on the tip and ring, which are there, but those are just used for the actual voice communications. It's on the E&M wires. They're also referred to as leads, so E&M leads. So we have the 3 different types of address signaling for E&M: wink start, which is the most common, and delay dial. Immediate start, the calling side goes off hook on the E wire, and it waits for a short but fixed length pause, and then it sends DTMF. So it immediately starts sending DTMF after a short pause. It doesn't wait for any return indication that it's okay to go ahead and send. Wink start is the most common because this is almost like connection-oriented TCP. We know that the other side is ready for us. So the calling side goes off hook on the E wire. It waits for a short off-hook pulse, or electrical pulse, which is basically known as the wink, on its M wire, and then it begins sending DTMF over the E lead. Delay dial, the calling side goes off hook on the E wire, waits for a short fixed pause, and then it looks on the M wire, believe it or not, to see if the called side is on hook. If it is, it sends DTMF. So basically on hook is hung up, right? Basically, we want to make sure that the other side isn't already in use, like it wasn't getting ready to call us or something. Okay, but if it's not getting ready to call us, that is, it's on hook or hung up, then we go ahead and send our DTMF. But if the called side is off hook, then we wait until it goes on hook and then we send our DTMF. So some people can use this as a form of like error correction to make sure it's safe to send. But wink start is the most common. Common configuration for E&M and camera trunks. For E&M, obviously we say signal, immediate, or wink, start, and then or delay dial. Operation 2-wire or 4-wire, and this is where I was saying this would be analogous to the 4-wire or 8-wire in terms of how many actual wires are used, but it's called operation 2-wire for two wires or a pair for the E&M lead, and 4-wire if there are 2 E's and 2 M's, so 2 pair of wires used, or 4 wires total used. And then we say the type of signaling, or type of E&M actually. Is it type 1, 2, 3, 4, 5, or SSDC5? CAMA, for emergency services, we will state a form of ANI mapping. So calling number mapping, maybe an area code or geographic code. And then we'll state, and this is actually something that we'll negotiate with the carrier, but signal CAMA, and then these are the actual commands. So whenever I put a parenthesis on the outside of something, I'm saying that this is, you fill in the blank with whatever you want here, a DN, a number, a tag. But if I put in terms of this Courier new font and left bracket, and then a value, a pipe, a value, a pipe, a value, a pipe, whatever, and then a right square bracket, that's saying these are the actual values, and you would put one or the other or the other or the other in as your actual values. Okay, I'm not going to get into exactly what they mean. This basically deals with 7-digit dialing. This deals with NPA, which I mentioned is area code, NPA NXX. So this is area code, and then central office prefix, and then the subscriber code or office code. Okay, but these are the different formats that the carrier, that the PSAP, the public safety answering point that you're connecting to via the carrier, via the central office, might expect to see information transmitted. And so you would negotiate that with them. Let's look next at the DTMF keypad and frequencies. So I really don't think you're going to have to remember all 8 of these frequencies. We have 4 down the left and 4 across the top. Okay. But it is good to know, you know, I can't imagine them requiring you to remember 1209 hertz and 1336 versus, wait, was that 1335 or 1336? It's important to know the concept of DTMF. I don't think you're going to have to remember the exact 8 frequencies. I would have a tough time doing that. But in fact, I don't remember the 8 frequencies exactly. But it is important to understand the concept. So the way this works, if I have a digit 1, this is going to play the frequency 697 along with the frequency 1209. So 1209 hertz or cycles per second. This would also be, you know, 1.209 megahertz. But anyhow, 1209 hertz and 697, it's going to combine playing those two frequencies at the same time. Sometimes this will be written as 697 plus 1209. It doesn't mean add those two frequencies together and play the resulting number. Okay, so it's not, what would that be? 16, 9, 10, so 3, 9, so that would be 1916, I think, if I did the math quickly right. I think it would be 1916. It doesn't mean play that frequency. It means play the 697 frequency and at the same time play the 1209 frequency. Thus the dual tone using multi frequencies or using two. Okay, so it's playing both those at the same time. That's how the sound of the 1 is generated. Okay, so if I wanted to play a B signal, I would combine playing the 770 hertz frequency along with the 1633 hertz frequency at the same time. So it's a matricy. Taking a look at call progress tones. Again, I don't think you're going to have to know the exact frequencies and on and off, but it's a good idea to know basically what the call progress tones are. And you might want to review this. It might be something that you want to review over and over, you know, right before you go into the exam, because they could ask you about it. I think it's a little cruel if they did personally, but, you know, might be good to know. So anyway, if we're playing dial tone, that's the frequency. Again, it's a multi-frequency, but it's 350 and the frequency of 440 played continuously and on and off. Okay. If it's continuous, there is no on or off. But if we have a busy tone, that typically sounds like beep, beep, beep. So that's the half second on, beep, but then it's a half second off and it goes back and forth. It alternates between the on and off at those intervals, as long as you have the phone off hook and dialed someone that was busy. Now, busy and reorder tone are often confused in people's speech. People often say, oh, I got a busy tone, when what they really mean is they got reorder. Reorder means the call couldn't be completed properly. Busy means just that. The call is completed just fine. It's just that the far side was busy. Reorder does not mean the far side was busy. It means the call couldn't work for some reason. Okay? So, but dial tone are these two frequencies played continuously. Busy tone, as I just gave you the lovely monotone example of, is 480 plus 620 hertz. Played for half a second on, half a second off. Ringback. And again, these are actually North American numbering plan call progress tones. So CP tone US. This is going to be different frequencies and different on-off cadence in different countries. But this is the US. So ringback is 440 plus 480. On for 2 seconds, off for 4 seconds. Congestion, which you probably don't often hear, is 480 plus 620, the same as reorder, if you'll note. Actually the same as busy, and that's why people often confuse reorder and busy, because they are the same frequencies. However, busy is quite noticeable. On for half a second, off for half a second, whereas reorder is on for 0.3 second and then off for 0.2. So it's much quicker. Okay, so reorder probably sounds like beep, 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 whereas busy is beep, beep, beep. Anyway, you're done with those. Receiver off hook on the other end. so they couldn't complete the call. Something that doesn't happen too much anymore. It used to happen plenty when I was a kid in the 80s. Are 4 different, fairly high pitched frequencies at, well, not really that high, at on for 1/10 of a second and then off for 1/10 of a second. So very fast. So anyway, just good to know. Moving on. Look at a digital voice circuit review. First of all, we have T1 CAS, E1 CAS, and ISDN. So T1 CAS uses time division multiplexing, or TDM, to transmit digital data, which is voice, over 24 time slots, also referred to as channels, using channel-associated signaling, or CAS. All the channels are used for both voice and data. E1 CAS uses time division multiplexing, or TDM, to transmit that voice or digital data over 32 time slots using channel-associated signaling. However, only 30 of those 32 are used for actual voice, 1 is used for framing, and 1 is used for signaling. So E1 is quite a bit different than a T1. It's not just that it has more channels. ISDN, or Integrated Services Digital Networking, uses something called common channel signaling. So channel-associated signaling means that I'm doing the signaling associated, well, specifically with T1, associated with the actual channel that's transmitting the voice. Okay, with E1, I actually do kind of have a single channel. With ISDN, I use something, but it is still referred to as CAS. With ISDN, I use a common channel regardless of which channel I'm sending the voice over. I use a common channel for all my signaling, for all my data. And by the way, ISDN can be used to send digital data, which can be voice, but it can also, such as video, or even just IP. You know, we can encapsulate a layer 2 protocol such as HDLC or PPP over ISDN as well. I've got a few different interface types. I've got primary rate interface, or PRI, and I've also got basic rate interface, or BRI. With a PRI, a primary rate interface, obviously we have broken down into T1, US and Japan, and E1, most of the rest of the world. A T1 PRI is actually 1.472 megabits per second with 23 bearer channels called B channels, and each of those are 64 kilobits per second. By the way, we're going to get very technical here on digital circuits, and this is stuff you need to know, okay, for the exam and certainly for real life as well. And one of those channels is going to be a 64 kilobit per second data channel, or D channel. With an E1, we've got 1.920 megahertz. I'm sorry, not megahertz, but megabits per second. With 30 of those, just like the E1 CAS, but 30 of those used for 64 kilobit bearer channels, and 1 used for a 64 kilobit data channel. Okay, then we have a basic rate interface, or BRI, and this has 128 kilobits per second using 2 64 kilobit per second bearer channels for the voice or data, and 1 16, not like a PRI where it has a 64 kilobit data channel, but it has a 16 kilobit per second data channel, or D channel. Okay, so the bearer channels are always 64 kilobits per second, and the data channel, or D channel, is 64 in a PRI, T1 or E1, but in a BRI it's 16. There's also something called NFAS, NFAS or NFAS, Network Facilities Associated Signaling. This is basically a method to allow us to aggregate multiple PRI interfaces grouped together, aggregated, to allow a single D channel to control all of the combined B channels. So maybe I've got 20 PRIs, right? And I'm a large company, I've got 20 PRIs, and I am using 20 separate data channels, but I could get another 19 B channels or bearer channels, almost another PRI, which is 23 if it's T1. Okay, so I can aggregate all of these 20 PRIs together and use a single D channel to control all 20, giving me 19 B channels back, or almost the equivalent of another PRI. So that's what NFAS is. You probably won't find it used too much, but it certainly can and is used in larger enterprise environments. Now, ISDN Q.sig, or Q.signaling, that actually says Q.sic. That should say Q.sig. Watch the magic of post-production. There we go, Q.sig. This is an enhancement of ISDN to provide rich supplementary services for PBX to PBX connections. So this is not used out to the PSTN. This is only used if I have, let's say, an ISDN PRI between, let's say, CUCM, and using obviously via a voice gateway, and also to, let's say a PBX that we're getting ready to replace, so we're doing a migration. But during that migration, we have a slow transition period, and some people are still on the older PBX, some people are on the new CUCM. Well, let's say, what happens if a call comes from the PBX, from Karen in accounting, and Karen wants to connect to Ben also in accounting, so she dials his number. Now, she doesn't know whether he's on the old or new PBX. She probably doesn't even know that there is a difference, except that maybe he has a different phone, maybe he doesn't. She knows that she has an old phone on her desk, and she's supposed to be getting one of these newfangled IP phones soon, though she's a little leery about it. She shouldn't be, but anyway, I digress. So I've got to keep you interested because this is a long module. But so she goes to call him, and he actually is on the new system. Okay, so he accepts the call. So the call has gone across the PRI, and it's over on the CUCM. Now, we only had one PRI to support the migration, but we've got 150 users on the old PBX and 350 users moved over to the new CUCM, Communications Manager. Okay, so we probably should have more than a T1, but we don't, and whatever. But channels are quite scarce and precious commodities, precious resources. We only have 23 bearer channels. So Ben decides, you know what? The person that can really answer your question best is Asher, and he's over in, whatever DN. So he forwards the number to that DN, but Asher's actually back on the old PBX. So now the call's gone back across the PRI, and now I'm using two bearer channels, one to come initially, which was fine between the two PBXs, but now the call's been transferred or looped, and this provides this big long loop. Some people call it a trombone because it represents the long loop at the end of a trombone. It goes all the way out across the PRI and then comes back, and we're using two B channels when really, I think we said Karen, whatever her name was, is now talking to Asher, and he's 2 cubicles down, doesn't really matter where he's at, he's on the old PBX. The call could have just gone directly. Well, Q.sig supports something called anti-tromboning. Anti-tromboning says, oh, we recognize through our enhancements that the call has gone out and then come back, which is something that doesn't too often happen on the PSTN, but certainly does between PBXs and tie trunks. And so we're going to go ahead and on the far side, I'm sorry, not on the far side, but on the close side, where the old PBX, assuming it supports QSIG, and anti-tromboning specifically as an enhancement to QSIG, it will then go ahead and cut off the communication through the two B channels, not use the ISDN at all, and then effectively get itself out of the loop after it's gone ahead and sent the forward back to the back to the original PBX to tell it to just connect Karen directly to Asher. Okay, and it does this during the call setup. So that's one of the nice enhancements to QSIG. Another one is that it carries MWI information. So if we've got a PRI connected into a voicemail system, and it supports QSIG, a legacy voicemail system, then this would be a nice addition as well. But those are some of the things, only a few of the things that QSIG provides. And also it's important to note that there's 2 layers of control for ISDN. There's the layer 2, which is known as Q.921, and layer 3, known as Q.931. Q921 uses a protocol called LAPD, LAPD, very similar to HDLC, in order to provide error detection and correction, and also something called terminal endpoint identifier. Okay? You might think of a TEI, or terminal endpoint identifier. You might think of TEIs as MAC addresses for ISDN. Okay, so they really are layer 2 addresses for ISDN. And then Q931, layer 3, is in charge, once Q921 is established and TEI, the terminal endpoint identifier, basically we've mapped the other side of the ISDN circuit to its layer 2 address, then we can begin mapping layer 3 to layer 2, right? Just like in IP, just like in frame relay with DELCs, IP to layer 2 DELC mapping, in Ethernet with IP layer 3 to MAC address layer 2 mapping. We can match layer 3 call setup to layer 2 TEI addresses. But anyway, Q931 sets it up, tears down, monitors the call, provides information about the call, user-to-user information. Oh, actually, these are 3 different types of Q931. We can have a user-to-user connection, something called a packet-switched connection, or a circuit-switched connection. Okay, this is something that typically the carrier provides for you, or that you know about in terms of whether you're using ISDN for data or for voice. So looking a little bit more in depth at T1 CAS, or channel associated signaling. So this uses something called robbed bit signaling. This is because we are robbing bits for every channel. We've got 8-bit channels. We're taking a single bit out of each channel in order to form the data that we're going to use to control the call and to provide information about the call, such as DNIS, called number. What bits are we going to use to pass that DNIS information? T1 CAS only sends DNIS by default. There's no calling number support. There's only called. And then signaling is either based on an analog loop start or ground start. Even though T1 is a digital type of a circuit, it can use analog signaling, such as loop start or ground start, or digital signaling, such as E&M types. Okay, we've already looked at E&M, the 3 types: the immediate start, the wink start, and the delay dial. Whether they're on an analog E&M or on a digital T1 CAS circuit, they basically use the same thing. Obviously, a T1 doesn't have an E&M lead per se, but it makes up for that with a similar functionality using the bits rather than electrical impulses. Now, if we're using E&M types, we support additions to the T1 CAS, and these are called feature groups. Feature group B and D, or FGB and FGD, basically do the same thing. The only difference being, what the carrier is supporting. But FGB and FGD, feature group D, they allow for both inbound and outbound calls, and on inbound and outbound calls, they both obviously have to support DNIS, otherwise we don't know where to route the call to. But they support calling number on inbound calls only, not on outbound calls. So if I'm calling out to the PSTN, then it's not going to send my calling number. Calls in from the PSTN, I will get the calling number. Feature group D, EANA, or what does it stand for? Exchange Association North America, I think. FGD EANA allows for both inbound and outbound calls, DNIS still, but ANI on outbound only. Okay, so the way I kind of remember this is supports ANI, okay, and then FGD EANA supports ANI anywhere in North America. ANA, anywhere in North America. So anywhere out in North America, out ANI is supported out. Okay, it's supported out to anywhere in North America. That's kind of the association I make. And then the other one has to be the opposite of that, inbound. It's a little dumb, but it's up to you. You might want to draw an association or not, but you might want to remember it. So line coding. This is getting into any T1 or any E1 has line coding and framing. Okay, line coding really deals with the electrical pulses that are sent on the actual line. This deals with the layer 1 functionality. So line coding can be AMI, which is the old version that both T1 and E1s used. It's technically called, and a binary 1 is a mark, a binary 0 is a space. There's also T1 only B8ZS and E1 only HDB3. And these are various forms of similar ideas. B8ZS, bipolar with 8-bit zero substitution. This again, most commonly used in North America and Japan. This replaces each string of zeros seen with a special pattern 000V, B0, VB. Okay, you don't have to remember the pattern. Just remember that, you know, B8ZS is used for T1 and replaces 8 zeros. HDB3 is what's commonly used for E1s in the rest of the world, and this uses, again, something similar, but it's high density bipolar of order 3. Okay, so this replaces any instances of 4 consecutive 0 bits rather than 8 0 bits with one of the following patterns, 000. The patterns probably aren't so important that you remember the exact patterns. Taking a look at T1 framing. This stuff is important, so you probably want to remember this. But with T1 framing, each time slot is 8 bits. There's 24 time slots times 8 bits, which gives us 192 bits. And we have an additional sync bit or synchronization bit at the end. So this gives us 193 bits per frame. Now, if CAS signaling is used, channel associated signaling, then 1 bit is robbed from each time slot. Remember, we use line coding and framing regardless of whether we're using CAS or whether we're using ISDN. Okay, so because we have 8,000 frames per second, and each frame we just said was 100, multiplication is what gives us 1.544 megabits or 1,544,000 bits per second. Okay, now if we group 12 frames together, we call this a superframe or SF, and this is the old way of doing things. We don't do this anymore. The new way, we group 24 frames together, and when we group 24 frames together, we call this an extended superframe or ESF. And this is what's commonly used today. With E1, it's not too terribly different, but it is a little bit different for sure. Each time slot again uses 8 bits, but there are 32 time slots, so we have 256 bits per frame. Notice there's no sync bit like there is on T1. Okay, so 8,000 frames per second is 200, or times 256 bits is where we get our 2.048. Now, time slot 0 is always reserved for framing, and time slot 16 is reserved for signaling. Remember, we use the framing on CAS and the signaling on our CAS as well, but we also use that same signaling channel for PRI as well. Okay, now by the way, this is counting, actually, yeah, this is counting canonically. Actually, I think time slot 16, let me correct this. There we go. If we're counting canonically, meaning we're starting at 0 as our first digit, then time slot 15 is actually the one reserved for signaling. If we're counting non-canonically, meaning we say 1 is our first channel, so in that case, time slot 1 would be reserved for framing, then time slot 16 would be reserved for signaling. And depending on where you look at this in CUCM or in iOS, even within iOS, you're going to see this referred to differently. So for instance, when I set up a PRI in, is it just the next slide? 2 slides, you're going to see that I define the PRI group, I define my D channel as 16, but when I actually show my D channel not on the controller, the E1 controller, but I actually see it show up as a serial interface or a voice port, it calls it 15. So when I define it in the controller canonically, when I see it show up in iOS and refer to it later, the iOS is counting canonically. So keep in mind that it could be 15 or 16 depending on where you're looking at it in iOS or CUCM, as well as the exams. So if you look at a given exam and it says, you know, here's your E1, here's your options for the D channel. Is the D channel 8, 15, 23, or 32? You know, well, the only good option there is 15. Okay, if that was replaced with 16, then your only good option is 16. Okay, but it depends on whether you're counting canonically or non-canonically as to how it's referred to, and it's referred both ways. Okay, and we use something called a multi-frame. So in T1, 12 frames was a super frame, 24 frames was an extended super frame. We don't have those here in an E1. We have 16 frames is one multi-frame, and it's referred to, it comes in either a CRC, cyclic redundancy check 4, or non-CRC 4 format. So taking a look at common configuration for T1 CAS and then PRI. First of all, it's always important when dealing with TDM, time division multiplexing, when we're dividing or dividing up our voice packets or data packets into segments and then sending them out and then reassembling on them on the other side based on time, it's a good idea that both sides agree on the same time, right? Because if not, if our clocks aren't in sync, well, then we're going to get out of order. And what's going to happen is if we don't have synchronized clocks, and this isn't layer 3 IP, is obviously POTS type signaling, T1 or E1. If we don't have these clocks in sync, then our clock's in sync with the telco provider. Obviously, the far end side, their clock's in sync with the telco provider. The telco should almost always be providing clock, but verify, because I've certainly worked with some that didn't provide clock, and you have to provide it on your side then. But either way, if we don't have those, then what we're going to see is if we do a show controller, T or E1, we'll see either line slips or clock slips. And we could experience garbled voice. Sometimes we could experience someone else's conversation. Sometimes it'll just drop the audio altogether and we'll have one way or no audio. Okay, so those are some common problems with clocking not being in properly. So first thing, network clock participate and choose the devices, whether it's a WAN interface card, even if it's actually a voice or WAN interface card. Choose the slots, the network module slots, the service module slots, the VWIC slots, the HWIC slots, whatever slots we have voice cards in, they need to have the network clock participate. That is, they need to participate in the network clocking. And by the way, iOS is intelligent enough that if you don't have a given voice card, service module or voice card in a particular slot or module, then it'll just bark at you and say, hey, there's no voice card there. So you can configure it, you can configure all of them basically, and it will just reject all except for the ones where there are voice cards present. But then in order to be our primary clock. Now, we're not going to get into right now, but if you do happen to have deployments where I've got, let's say, one iOS router or voice gateway that has PRIs or even T1 or E1 CAS and PRIs into multiple carriers, and well, they're not going to sync their clocks. So we need to have each one of our controllers synchronized to different clocks. Well, iOS does provide for that. We can create what are called TDM profiles, time division multiplexing groups or profiles, and then link various controllers to those profiles. That way we can synchronize our clock, our TDM clocks, with different providers. But we do need to have separate separate DSPs, because the DSPs have to be linked to the clock, and we need separate service modules or network modules to support those DSPs and then also to support those voice cards. So that's important, but if we do, then we can pool TDM groups together and use those separately, sync to separate provider clocks. But then we can't mix those DSPs. We can't share the DSP resources. We can only share DSP resources with synchronized clocks. Okay, it's all about clocking. So at least on the telephony side, the POTS side, and DSPs or PVDMs, that's what they do, is they go between POTS and VoIP. So it's important on the POTS side of their operation that they are synced to a clock. So, but this is our primary clock, network clock select. We're saying primary 1. We could also give it, another clock if we said maybe we have 2 controllers or 3 controllers, 3 peer. So if one goes down for whatever reason, we could say your secondary time, network clock select 2, use T1, 001 or something like that. Okay, so here we're framing ESF, extended superframe, line coding bipolar 8-0 substitution, and we're pulling our clock from the line. So what line? This line, the primary line. And who's participating? WIC 0, which is this one. Okay, if the carrier wasn't providing clock, or if you're doing a lab and you need back-to-back configurations, someone has to be the clock. Okay, so one of your controllers, maybe your PSTN emulator, the router that was behaving like it was the PSTN, you would have clock source internal. And then all of your other edge routers would be clock source line. Okay, DSO group 0 canonically and group 1. I'm defining 2 groups. I'm defining that time slots 1 through 12 are going to be used with E&M, and not just E&M wink start or E&M immediate start, because if so, maybe I'd do the whole range of 24. But this is E&M FGD, feature group D. And then the others are feature group D EANA. So what's the difference? They both send DNIS in and out, obviously, because whether a call's coming in from the PSTN or going out, it needs to be able to know where to go, where to route to. FGD, well, I remember that FGD EANA sends calling number anywhere in North America. So this is outbound ANI. So the other one must be inbound ANI support. And that's going to produce voice port 000 to coincide with the T1000, and then :0 to coincide with the time slot voice port 000:1 to coincide with the other DSO group. A DSO is a digital signal or digital circuit 0. Okay, so it is a single channel on a digital CAS circuit, DSO. If I have a DS, 1, that's equal to actually like a T1. If I have a DS3, that's similar to a T3. Okay, so but a DSO is I'm grouping together a number of DSOs or a number of channels. Okay. If on this controller I did channel group, that would be a data only. DSO group is a voice only. And then PRI obviously can handle both. So looking at the same controller, same framing and line coding, same clock, but instead of DSO group for CAS, I'm doing PRI group, and then 24 is the D channel, so this is counting non-canonically. But this produces voice port 000:23. This is counting canonically. It's the same channel. Just depends on whether you start at 1 or start at 0. Looking at common configuration for an E1, we still need network clock participate and select. So select my the interface that I'm going to slave off of, that who is going to be the master in terms of determining the clock, and then which interfaces will participate in that. I'm only going to really have one clock select, or at least I might have multiple, but only one at a time, the primary, unless it's down, but multiple interfaces will participate in that timing. So framing, most common is no CRC4, line coding HDB3, pull the clock slots, so group 0, 1 through 31, type And I could do E&M, but more common is R2 digital, R2 compelled, and I have to tack on ANI if I want calling, and E1 supports calling or ANI in both outbound and inbound directions. Remember, it's got that channel 16 or 15, counting non or canonically, respectively, that it has more bits to handle more signaling information like ANI in both directions. And it produces this voice port just like the T1 would. And then very similar to a T1, PRI group time slots 1-31. And this is actually segmented for me. It'll say 1-15, 16, 17 through 31. Okay, because that 16, or counting canonically, or I'm sorry, counting non-canonically beginning with 1, or counting canonically beginning with 0, 15, that is going to be the D channel or the signaling channel. So it produces the voice port 000:15. Okay, moving on from POTS signaling to VoIP call processing. So these are the stages of call processing inbound from an analog or a digital circuit. So first of all, in the PVDM, the Packet Voice Data Module, which is Cisco's DSP, the following occurs. First of all, the audio is sampled using something called Nyquist's theorem. We're going to talk a little bit more about that. Next, quantization happens. Okay, we're going to talk more about that. It's important to know what these are. I would imagine you probably will be tested on these. I believe, if I remember properly, although it's been at least 10 years since I took this exam, I believe that I was tested on these. Okay, this is just fundamental voice over IP. It's absolutely critical to know and understand, especially when it comes to troubleshooting. Okay, so keep that in mind. So first of all, we sample the audio using Nyquist's theorem. Next, we are quantization takes place. We'll talk about what that is in terms of approximation. Then encoding takes place. After we encode, then we can optionally compress. Typically, it just depends on the codec that we're using, whether compression occurs or not. And then finally, iOS is going to encapsulate the resulting encoded voice into the IP RTP payload. But this is all what happens it's doing a lot in there. This is on an inbound call from the PSTN. On an outbound call to the PSTN, or just to an analog or digital circuit in general, actually doesn't have to be to the PSTN, could be out to, let's say this is happening on the phone. Okay, that's got a DSP. It has to translate it into audible voice, or if we were getting it sample it from audible voice. So in a phone, a DSP, an IP phone, the phone itself samples your audio, then quantization takes place, then it encodes it, then compresses it, and then packetizes it. Okay, when it's going out to an analog or digital circuit, or just out to a phone receiver handset or speaker, iOS decapsulates or depacketizes the IP RTP payload and to the PVDM. The PVDM or DSP decodes the previously encoded voice and then modulates that. Okay, so actually creates the audible frequencies, which is effectively the reproduction of the original sound. So let's take a look closer at those 4 stages: sampling, quantization, encoding, and compression. So sampling of audio frequencies. Most human speech occurs in the frequency range of about 200 to 8,000 hertz, or 8 kilohertz. Now, human perceptible audio frequency range is about 20 hertz, which is actually called a low frequency effect. It's more felt than heard, technically. We don't really hear sounds too much below 100 hertz. We feel them, but regardless, it's said that we hear or sounds are audible from about 20 hertz or 20 kilohertz. But human speech occurs in the range of 200 to 8,000, or some people say 200 to 9,000. Most telephony, however, has always sampled in the range from 300 to 4,000 hertz, 300 hertz to 4,000. So it's cutting off about 100 hertz at the bottom end, the low end, and it's cutting off 4,000 hertz, a very large frequency of the high frequencies, the S's and the T's, what's called sibilants. Okay, if I'm very sibilant, then all of a sudden, and actually I have a de-esser on my voice processor, so I'm not sure necessarily how much you can hear that, but if I'm very sibilant, whenever I do that, I can see it, the de-esser kick in. But those are in the very upper range. Okay, and that's actually known, 4,000 to 8,000 or 4,000 to 9,000 is known as the presence range. But anyway, telephony typically doesn't sample there. So why doesn't it? Well, we reduce the bandwidth that we need to transmit this, even over analog or digital circuits, by sampling only part of the frequency. And since it did only sample part of the frequency, Nyquist came up with an algorithm, I think his name was Harvey Nyquist, that allowed us to sample this spectrum of audio frequency. So since 4,000 hertz was the max desired frequency, he stated that we should sample it twice as fast. Okay, so we cycled it, or we sampled it at, and for those that don't know, hertz basically means cycles per second. So basically we're sampling audio every 1/8 every second that audio is transmitted. Okay, so 8,000 samples. That's a lot of information. I thought the whole idea was to reduce the bandwidth that we needed, or not really reduce, but you know, if we're talking about back in the 50s and 60s, transmitting this digitally, then we had very limited bandwidth to work with to begin with. So 8,000 samples, that's a lot. How are we going to fit that all into a small, you know, digital signal, even like, let's say ISDN, where we're using something called PCM, or pulse code modulation. How are we going to sample, which actually G.711 is based on PCM. And if you note, if you've drawn the, if you happen to have drawn the, what's the word I'm looking for? The link between the two, ISDN uses 64 kilobit per second channels. And how fast is the default signaling rate of G.711? Oh, that's right, 64 kilobits per second. Interesting. They basically use the same technology. So anyhow, and that's PCM. But so anyhow, 8,000 is a lot. Okay, so what are we going to do to limit that? We're going to perform quantization. Quantization is a process that constrains a large set of values into a relatively small workable set of numbers. What does this mean? Kind of that we're sampling the sampling. We're basically taking an approximation of a very large continuous range of values that was obtained from the 8,000 samples per second, and we're approximating them. So that we think accurately, hopefully accurately, represents the original sampling. Okay? So that's the process of quantization, is to approximate the large 8,000 samples per second into a smaller, more workable set so that we can encode those. And when we do the process of quantization, companding is an algorithm that takes effect for PCM into G.711, and it comes in two 8-bit flavors, mu law and A law. Mu law, used in North America and as well Japan, provides for better low-level signal-to-distortion ratio. However, A-law, used most everywhere else, provides for a better dynamic range of audio frequency. Law country connects to an A-law country. It is actually the responsibility of the mu-law country to convert. Okay, so this is one place where the U.S. doesn't dominate. If we are connecting to pretty much everywhere else in the world, it's our responsibility. We have to, the burden of conversion is on us, not on the rest of the world. So let's look at encoding of the companion, the encoding process. So simply put, we're basically now taking the smaller set of values, the quantization values, and we're putting those into decimal integers, the result of the companded quantization. So we're putting those into a binary 1 or 0. And then optional compression can be performed into various codecs. Codec is compressor, decompressor, and such as G.729, the Internet Low Bitrate codec, the Internet Standard for Audio codec, etc. So various compression mechanisms.